Okay, so today we are going to study about interval estimation. Interval estimation is a parallel topic to point estimation. So the methods of point estimation that we have learned in previous lecture, it gives one value of the parameter given the data for some unknown value of the parameter which is not known. But interval estimation usually provides an interval for one unknown value of the parameter. So the fundamental idea is this: the value of the parameter is unknown but fixed. Then given the data, point estimation provides a particular value for the same. But the concern is here that we have seen consistency, we have seen unbiasedness, all those properties. But say, for example, if the estimator say Tx is continuously distributed, then probability of Tx equals to the true value of parameter. This thing will happen with probability 0. Okay. And that is the thing is not very much recommended. I mean, recommendable in the sense that people often want to have an interval, then a particular number. For example, it has also application. It has. Yes, please.
The screen is too much, sir.
I don't know what
Sir,
happened.
it
The
is
screen
okay.
is fine.
It's okay for
It's
us.
fine. It is fine.
It's fine. Actually, I don't know. I complained to CIC also. But in other course, it is not happening. Only I face that you are in your session, it is having trouble. I'm teaching another course. There is also 170 students. This is quite surprising. Let us see. Okay, so only tomorrow. Then it will be over. So, yeah, MS Team has some issues in the recent days. That is true. Okay, so what I was saying is that it has an other application. For example, if you see that medical report, so say for example you go for hemoglobin count, or for blood sugar fasting or with food, or for creatinine level, or for platelet count. So they give an interval. If they just provide only one number, then none of us will be able to match that number. Does it mean that we are ill? That is not the case. Most of us are healthy, uh, but if only one number is given there, none of us will be able to meet that, and because of that, we cannot conclude that we are ill. So another application, say for example, medical report. This is one. Then for given height, the weight. So height weight distribution. So suppose you are 5'5". This much should be your weight. Only a particular number. If it is written in front of your gym, say, none of us will be able to exactly match that number. That doesn't mean that we are unfit. Okay. There is some interval. Below that, some other kind of treatment. Above that, some other kind of. So these kind of situations are necessary. Even, say for example, when we make different policies, then also we often need some interval. If the value lies within that interval, we will go by some scheme. If it doesn't fall within that interval, we will go by some other scheme. So all these kind of examples are there. So, and all of them are in some sense of interval estimation problem. Okay. Now, the question is this, that for the parameter value, we are willing to obtain an interval. So hence for a parameter value, hence for an unknown parameter value, we are willing to have an interval given it. Now, I have an interval and there is some unknown parameter. So that parameter may be within that interval or out of that interval. So the probability can be either 0 or 1. But often we give the statement like this, that 95% confidence interval kind of thing. So from where this 95% comes? Can anyone try to explain? Or 90% confidence interval or 99% confidence interval?
Normal distribution.
Say again.
Normal distribution. Like in normal, we had different mu plus minus 3 sigma like that.
Yeah, but here you see that you have an interval, say A to B, and there is some unknown parameter theta, which we don't know from the parameter space. Then either theta will be within this interval or it will be out of that. So either if it is within this interval, it is 1. If it is out of that interval, it is 0. From where this 100 into 1 minus alpha percent Ci, from where this quantity comes.
So do we assume some distribution of theta over the parameter space?
No, no. Theta is fixed. Already declared. It is fixed. We are not doing Bayesian. If theta is fixed, then what can be variable?
A and B.
A and B, yes, correct. So the interval is a random interval here. Keep it in mind. The interval which we estimate is a random interval. That is the key point of this interval estimation problem.
Sir,
Yes, please.
sir, in height weight distribution, like we will be given the height, right? So that is the given data.
That is given data.
And we want to estimate weight. So what is the parameter? Means fixed parameter. What is that in this case?
Okay, so here height and weight has a different story. Say for example, suppose your height and weight has this relation. So here I so that's why I have written it in a other application. So say for example, I'm writing here that your weight has this relation with height, alpha plus beta into height. So suppose your height is properly measured 5 foot 5. Beta we don't know, alpha we don't know. But given this height, there would be some true value of alpha and there is some random error. So we can have expectation of W as alpha plus beta into 5.5 for say your case. Now we are willing to have a confidence interval of this number where alpha not known, beta not known, alpha we have to estimate from the data, beta we have to estimate from the data, and they will have their own distribution. They might have dependency when we will estimate, and as a consequence we can have a confidence interval of this number. What should be your expected weight? We can have a distribution of your weight, and from there we can have the mean part of it, and that parameter for that parameter value we can have an interval. Is it clear now?
So the parameter here is weight, right?
No. Parameter is not weight. The expected value of the parameter, the parameter is the expected value of the weight, which is a parametric function. Yeah.
So how is that fixed? Because alpha and beta are means varying. So we are saying that the value of parameter is unknown but fixed.
Yes, of course.
Then alpha and beta will also.
Expectation is fixed. This expectation is fixed, but the interval that you will get for this expectation, that is not fixed.
Okay, sir.
Okay. So if you do the survey in your class, you will get some value of alpha, some value of beta, and from there, and according to their distribution, you will get some number. maybe in other section, if you conduct the same survey, you will get some different value of alpha, you will get some different value of beta, and some different estimate of their variance, and as a consequence, the estimated value of the mean will be different, and the interval that you will get, that will also be different. Is it okay now?
Yes, sir.
Sir, can you explain it with an example?
Okay, yeah, this is an example.
With numeric.
Numeric. This is the tragedy of your generation. Okay. So suppose, okay, let me explain the usual method, then I will come back to it and I will explain it, because otherwise it will be more difficult to say just now. So here what we are trying to say, that random interval that we get, they are different for different samples. So for example, here I have drawn 50 different samples with sample size 8 from normal distribution, normal 0, 1. That I know as I have generated the data. Method, the method I will explain. Based on some method, I am obtaining this estimated interval, which is supposed to contain or engulf the true parameter value, which is 0, within that interval. But here, with this example of 50 simulations, you can see that all these black line intervals, they are containing the true parameter value. They are containing the true parameter value, but those red lines, this is also an interval. It is not containing the true parameter value. So a certain proportion of the interval will contain the true parameter value, and few or another proportion of the interval will not contain the true parameter value. So the proportion which will contain the true parameter value is referred as, in this case, 1 minus alpha. And if you convert it to percentage, 100 into 1 minus alpha percent cases, the true parameter value will be in the estimated interval. So as we have done point estimation, a similar way we will do the estimation for this thing and estimation for this thing, and this will become a random variable. This will also become a random variable. So this interval will become a random interval. That random interval is supposed to take the true value of the parameter within it with a certain probability, and that probability is 1 minus alpha, pre-specified. So now I'm going to describe the method for this simple case. So this is the idea that consider a pair of statistics, Lx and Ux. Both of them are individually a function of parameter, a function of data or known parameters, such that the true value of the parameter belong to that interval is 1 minus alpha. And 1 minus alpha is pre-specified number. Then 100 into 1 minus alpha percent confidence interval of theta is considered to be Lx to Ux. Lx usually stands for the lower bound of the interval, and Ux for the upper point of the interval. So this is how we define. Now let us go for this example. X1, X2, Xn are IID random variables with normal mu sigma square. For sigma square, first for the time being, let us assume that it is known. Then let us try to see that how we get this lower bound and the upper. So X1, X2, Xn, they are IID normal mu sigma square, mu unknown, sigma square known, and we are looking for obtain uh, 100 into 1 minus alpha % confidence interval of mean. Okay, the mean, just simply the mean. Now, here you know very well that you can estimate mu with x bar. And also you know that x bar follows normal mu sigma square by n. Okay. Now, if you do the standardization, this will follow normal 0, 1. So if this is the distribution of Z, I am considering this is Z alpha by 2 and this is minus Z alpha by 2. So within this region, probability Z will belong, that probability is 1 minus alpha. So this region is alpha by 2. This region is also alpha by 2. As simple as that. Then it is trivial that probability Z alpha by 2 minus Z alpha by 2, that is 1 minus alpha. I hope there is no doubt here. Now, rest part are trivial. You write down the expression of Z, x bar minus mu divided by sigma. Then do the side change in such a way that mu will be in the middle, rest of the thing will go to either right hand side or left hand side. So multiply by sigma, divide by root n, then subtract x bar, then do the multiplication by minus 1. So all this thing you do. After that, you will come up with x bar minus sigma by root n, Z alpha by 2, mu x bar plus sigma by root n, Z alpha by 2. This quantity is 1 minus alpha. Now you can see that Lx, it is a statistic. Sigma is known. Z alpha by 2, everything known. Ux is also statistic. Sigma is known. N known. Z alpha by 2 known. And what is the interval, length of the interval? Which is 2 times sigma by root n, Z alpha by 2, which goes to 0 as n goes to infinity. So if you take more and more sample size, the interval will be smaller and smaller. Now, tell me if you have any query here. Any query? Any doubt? this standardization, this is often known as pivoting. So making the distribution free from parameters. This is what we have done. After that, from the known distribution, you do rest of the steps. Tell me if you have any query here, because this is the basic thing. The rest of the thing will be a subsequent application of this idea. Hello? Is it clear for everybody?
Yes, sir.
Okay, very good. If it is clear for everybody, then let us go for other versions of it. Now you consider the situation when x1, x2, xn are IID, normal, mu, sigma square, both parameters are unknown. Okay, obtain. Now here you can see that if you change from one sample to other, the value of x bar is going to be changed, and as a consequence, the lower bound and the upper bound of this interval are going to be changed. Whatever interval you will get from your data, whatever interval I will get from my data, they can be different. But in a probabilistic sense, if we follow the same method, your interval, your method should satisfy that the true value of the parameter within your interval will be with probability 1 minus. For a given interval, for a fixed value of the parameter, it will be either within that interval or it will be out of that interval. But the method by which you are constructing the interval, what is this one, it must maintain that with probability 1 minus alpha, it will engulf the true value of the parameter. That is the idea of confidence. Now obtain, say 95% CI of mu. Okay. So go by the same way that mu hat is x bar. X bar follows normal mu sigma square by m. Okay. But okay, then you do the standardization. Z equals to x bar minus mu by root n sigma. That follows normal 0, 1. But sigma is unknown. Okay. Then you have to estimate sigma. So sigma square hat equals to 1 upon n minus 1 sum over xi minus x bar whole square I ran from 1 to n. Is it okay? Now we can plug in the value of sigma here. So as a consequence, what we will get, t equals to root n x bar minus mu by sigma hat, which is root n x bar minus mu whole divided by sum over I running from 1 to n xi minus x bar whole square whole divided by n minus What will be the distribution of this statistic? Hello? What will be the distribution of this statistic?
The T distribution.
T distribution, degrees of freedom.
n-1.
So now again, routine job. T distribution, n-1 degrees of freedom. This is tau alpha by 2 n-1. This is also tau alpha by 2 n-1 with negative sign. This region is alpha by 2. This region is alpha by 2. This area is 1 minus alpha. So you can write probability minus tau alpha by 2 n-1 t tau alpha by 2 n-1. This is 1 minus alpha. As simple as that. Replace the value of t, do the side change, get the answer. So root n x bar minus mu by sigma hat tau alpha by 2 n-1 minus tau alpha by 2 n-1 probability 1 minus alpha. Again, mu is in the middle, so x bar plus sigma hat by root n tau alpha by 2 n-1. Here x bar minus sigma hat by root n tau alpha by 2. Probability of that is 1 minus alpha. So this is Lx. This is a function of x. This is a function of x vector. This is Ux. Yeah. So is it okay now? But remember, when sigma unknown, you have to estimate it. So this is the estimator of sigma, or more precisely, unbiased estimator of sigma square is this. We have used that thing and we got this is as a confidence interval. So procedure is same. First you obtain by which you can estimate mu. Then you go for standardizing it or pivoting it. And then you check if there is some unknown parameter. Well, here sigma is unknown parameter. Estimate that, plug in that value. Then you obtain the distribution of the statistic. Then you study the distribution. You take the lower alpha by 2 point, upper alpha by 2 point. And from there, you write down this relation, replace the expression of the statistic, keep the unknown parameter in the middle, and do the side change. This is the simplest way. I mean, this is our case. Please.
Sir, we wanted to find an interval in which mu lies with probability 1 minus alpha, right?
Yes.
So means instead of means we first estimated mu with x bar.
Yes.
And then so it is equivalent to finding an interval in which x bar lies with probability 1 minus alpha.
X bar lies with x bar. No. X bar can lie in many intervals with probability 1 minus.
So like we are first converting into normal 0 1, and then we are just doing algebraic manipulation right here.
Yes, of course.
But how will we come to know that from which algebraic manipulation we will get the corresponding interval?
Well, there are, I mean, more advanced version of it. There are, say for example, if you know that this thing follows normal 0 1, so first of all, you need to make a transformation in such a way that this side you will have no unknown parameter. This is the pivoting. That part is important. After doing pivoting, this is not the only interval which contains contains the 1 minus alpha probability.
Yes, sir. Means many
Yeah.
intervals are possible.
Many
So
intervals are possible. That derivation we are not doing in this course. There is called the minimum length interval estimation, such that within that interval you can obtain 1 minus alpha probability. So for normal distribution, this is eventually becomes the best possible minimum length interval. That is a second layer of problem that is not incorporated in this course.
okay, sir.
Okay. So because of the symmetry, I have taken alpha by 2 this side, alpha by 2 this side. I can also take alpha this side and from here to infinity. But that will not be a good interval. An interval with infinite length. With the same rate, I can do that, definitely. But that will not be a good thing to. So we always, our target, if you are really interested, I will always recommend that do an inference course. It will be really helpful for you, and your idea will be completely clear there, that why and how the statistical tools are used. And that will be helpful for your any discipline. Your way of thinking will be so changed that your logic and practice will be sharp enough. Okay, anyway. So this is how it works. Typically, it becomes the best possible interval for this symmetric distribution. Another example we can go for quickly, which will not be symmetric. So if I want to estimate, want to get the confidence interval of sigma square. Okay, so let us see that. Okay, so again, same thing. X1, X2, Xn, IID, normal mu sigma square. Both parameters are unknown, and obtain 95%. Here I am everything writing in terms of alpha, so 95 alpha equals to 0.0. Here also. Here I have written 1. You can put any value of alpha between 0 and 1. It will not be a problem. 95% CI of sigma. So now the problem is a little bit different because we have to estimate sigma square, and the distribution that we will get, that is not symmetric. So now, okay, not at all a problem. Sigma square hat, you know, that is 1 by n minus 1 sum over xi minus x bar whole square, I running from 1 to n. Okay. So first we start with this expression that sum over xi minus x bar whole square, I running from 1 to n. 1 upon sigma square, that is following chi-square distribution with n minus 1 degrees of freedom. And this chi-square, it is not a symmetric distribution. So this is chi-square n minus 1 degrees of freedom. So here, again, we are trying to truncate in this way that this region is alpha by 2 and this region is also alpha. Okay. Now I will call, if I call this point as chi-square alpha by 2 n minus 1, then what will be the corresponding notation for this point? If I call, if this region is alpha by 2, then I call this point, usually this is known as the upper alpha value. That means from this point up to infinity, if you integrate, that probability will be alpha or alpha by 2, whatever given in the sum. So what will be the name of this point? If we go by this,
1 minus alpha by 2 comma
yes.
minus 1.
Yes, that is 1 minus alpha by 2. Now, this part is same, that within this region, this chi-square n minus 1, that will fall. That probability is 1 minus. Now, I hope you can understand the job is trivial. That chi-square n minus 1 alpha by 2 n minus 1 chi-square. You always, whenever you see the chi-square table, you always check how they have given the table. Whether they are giving the table from minus 0 to certain point integration or certain point up to infinity integration. You always read the footnote or the header of the table, how the table is constructed. So here, this is alpha by 1 minus alpha by 2 n minus 1. That probability is 1 minus. Now you write down, oh, okay, so this expression, let us, anyway, let us call chi. So write down this expression here. Sum over xi minus x bar whole square, 1 upon sigma square. So chi-square alpha by 2 n minus 1. Chi-square 1 minus alpha by 2 n minus 1. Now again we have to do side change in such a way that sigma square will be in the middle, rest of the thing will go in the other side. So here you can see that if you take the reciprocal, all this direction will change of the inequality, and then you need to do the side change. So here you will get xi minus x bar whole square, I running from 1 to n, also xi minus x bar whole square, I running from 1 to n, and here this thing will come chi-square alpha by 2 n minus 1. Here this thing will come chi-square 1 minus alpha by 2 n minus 1. Don't do mistake here. You can see that this quantity is less than this quantity. Here numerator you have same expression. So if you divide by something which is less in magnitude, you will get larger number. If you divide with something which is more in magnitude, you will get the less number. So this will be Lx, this will be, this is the 1 minus alpha % confidence interval. Keeping both sides alpha by 2, alpha by 2. you can also say that from 0 to, if you take from this point up to alpha, that will also be an possible. So, okay, alpha here is 0.0. We can take it. So, any query? Any query? So all these three important distributions you have seen here, normal, t, and chi-square, they are being used for this interval estimation purpose. And also you can do different cases like suppose your score in mathematics and your score in statistics. For that kind of situation, you can deal with, you can check whether the mean are same or not, or maybe the mean of your section and mean score of this subject in your section and another section, whether they are same or not. On the other hand, you can also check whether the variances are same or not. So maybe this kind of thing we will talk about tomorrow when we touch some part of testing a little bit. All those things, you need to construct a statistic for which you have a distribution which is free from unknown parameters. And the study of sampling distribution has an immense application there. So most of the cases, it will be either converted to normal, 0, 1, or t, or chi-square, or f. Okay. So if you are going for the comparison of variances, you need to go by the ratio of variances, and that estimator will turn out to be f strategy. Well, now let us go for the example that we were talking about, the height weight distribution. So now, this is usually a regression problem, that your weight is some alpha plus beta times your height, okay, plus some error. It is usually assumed in this way that the error, so for different individual you will get the observation, WIHI, I running from 1 to up to. Usually this is the assumption, and this error are IID, normal, 0, sigma square, where sigma square unknown, and also alpha beta unknown. So first, what it is done, so get the data like this, paired observation WIHI, estimate, get the data, then estimate alpha, beta, and sigma square from data. Then predict, so W y alpha hat plus beta hat H. Now in this formula, now this is a function of data, this is also a function of data. In this formula you plug in your height. So this will, if you plug in your height, then this will be the predicted value of your weight. Now if you look for an interval, okay, then what you have to do? Then you need to study the distribution of alpha hat. You need to study the distribution of beta hat. Then you need to know that what, say, if I say this is W hat, then we need to find out the distribution of W hat. And we can, so if you go by this, you will get that W hat will be following some normal distribution. We can obtain (95% CI) of the expected value of W. This is parameter, and it can be shown that the expected value of W hat given this number, it will be alpha plus beta into 5.5 if you have plugged in 5.5 there. So it will be, the mean part will be this, alpha value is unknown, beta value is unknown. So this parametric function is unknown. This parametric function has a point estimate this, but if you go for an interval estimate, then from the distribution you will be able to obtain this quantity, that alpha plus beta 5.5. This will be bounded by L, say W vector, height vector, and U W vector. So you will be able to obtain a lower bound as a function of data. You will also be able to obtain an upper bound as a function of data, and it will engulf the parameter value as a function of alpha and beta and this plugged in height with probability 1. Now is it clear? To obtain this distribution, you have to do some amount of work. That is 2-3 lectures on this. Is it okay now? What is the motivation and
Yes,
what
sir.
Yeah, so if you really want to know this, come to regression course next year or next to next year, whenever you will have the time and slot, I will teach you. Okay, so tomorrow we will talk about little bit of testing of hypothesis, and we will finish the course. Anything else? Hello? Okay, then fine. See you tomorrow, early morning.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.